Assalamualaikum and good day to all of you. So today I will brief you on lab 2, which is control single phase rectifier with R load. So this is your lab sheet. Okay, so for learning outcomes, in the end of the experiment, students should be able to construct power electronic circuit, measure and sketch output voltage and current, and then calculate the performance parameter of power electronic circuits such as average and RMS of voltage, current, and also output power. So these are the equipment or component we are going to use today. Okay, and then for the synopsis and theory, you can refer or you can read by yourself from the lecture notes. Okay, so next I will proceed to the procedure for this lab. Okay, so this is your circuit of control half-wave rectifier with resistor load. So you have power supply, and then you have power tristor, or here we use SCR. So SCR stands for silicon control rectifier 2N1599, and then you have resistor as your load. And then one more component we are going to use today to control the firing angle is pulse, voltage pulse. Okay, so next I will show you how to simulate this circuit. Okay, so this is your multisim. First of all, you have to get your power supply, ground. So these are the basic components you need in your circuit, and then you need one resistor, so any value because we can set later. And then for today we are going to use SCR. So go to family SCR and then find 2N1599. So this is your diode. Okay, so one more component we are going to use today is to control the firing angle, where we have to use signal voltage source and then pulse voltage. Okay, so these are 5 items to build control half-wave rectifier. So rearrange your component. Okay, and then connect or complete your circuit. Okay, so voltage pulse you have to connect to your diode. Okay, so and then your ground, and also here connect to ground. Okay, so this is your complete circuit for control half-wave rectifier. And then you have to set the value of your supply first. So refer to your lab sheet. You have to set to 240 with 50 Hz frequency. Okay, we pick. And then for resistor, you have to set to 680 ohm. And then, okay, so for voltage pulse, so refer back to your lab sheet. So the voltage pulse setting, initial value is 0, pulse value is 5, pulse width is 0.001, and then period is 0.02. So where you want to get the value of period, so period is 1 over f, your frequency is 50, so 1 over 50 you will get 0.02. So first set all your pulse voltage pulse setting here. Initial value is 0. Okay, double click this and then initial value is 0. Okay, pulse width is 0.0001. Period is 0.02. And then what else we need to set? Pulse value is 5 volt. So pulse value is 5 volt. So these are the setting you have to set at your pulse voltage. So others, please do not change anything. Okay, so this is your initial value, and then your pulse value. This is your pulse width, and then this is your period. Okay, next. Okay, so finish procedure number 4. We proceed to procedure number 5. Okay, so set the firing angle to have a value of 0 by setting the time delay. So record the time delay and the value of RMS, average of output voltage and current, and summarize your result in table 1.1. So this is your table 1.1. First, we have to set the firing angle to 0. So this firing angle first start with 0. Okay, 0 degree. So how to find the time delay? So for time delay, we have to use this formula. Okay, time delay is equal to alpha, or your firing angle, over frequency times 360 degree. So first, we set the firing angle to 0. So 0 degree times 50 Hertz times 360 degree. So 0 divided by anything, it will be 0 second. So this is the value of your time delay for firing angle with 0 degree. So your time delay here will be 0 second. Okay. So go back to your simulation. Okay, so time delay here set to 0 for firing angle 0. Okay, so as usual, we have to use the oscilloscope to capture the waveform of your current and voltage. So channel A to measure the input signal, and then channel B to measure the output. So this is your output. Okay, you can straight connect to here, and then get another one. Okay, connect your negative probe to ground. Okay, and then for this one, you have to measure the current. So how to measure the current? Same with lab 1, you have to use current probe, and then negative go to your ground. Okay, so display all your oscilloscope screen, and then you have to run your circuit. Okay, to see the difference from input and output, you can change your probe color. Okay, so adjust your scale. Okay, and then next for current, also adjust your scale. Okay, so this is actually the waveform with firing angle 0 degree. So after this, I will show you another example with different firing angle, so you can see the difference. Okay, so this is your waveform with 0 firing angle. Okay, next you have to record all the value here. So V output average, V output RMS, I output average, and I output RMS. So how to get this one? This one also you can use this measuring probe. Okay. So this will be your reading of, so okay, so this will be your reading of your RMS and average value. Okay, and then you can complete this table. So all the reading you can get from the measurement probe. And then how to calculate your PDC and PIC. So this is DC power and AC power. So for this one, you have to use this formula. So PDC equal to I DC times V DC. Okay. And then for PAC, so I write it here. So PAC is equal to I RMS times V RMS. Okay. So these are the formula to get power DC and power AC. Okay, so you have all this value, and then you can find PDC and PAC. Okay, so finish procedure number 5, and then for procedure number 6, with increment of 30 degree, increase the firing angle until its maximum value. Repeat the procedure 5 to complete the table 1.1. Okay, so you can fill in your table but with the 30 degree increment. So start from 0. So at 30 it will be 30 degree, 60 degree, 90 degree, and then 120 degree, 150 degree, and last one 180 degree. Okay, so after you identify or set your firing angle, you have to calculate the time delay. Okay, so for example, I'm going to show you how to get this value, all this value for firing angle 90 degree. Okay, so for firing angle 90 degree, so you have to calculate time delay. So 90 divided by your frequency is 50 times 360. It will be 5 millisecond. Okay, and then you have to change your time delay. So you only need to change the time delay. So time delay here, okay, change to 5 milli. So this is your setting for firing angle 90 degree. Click OK and then run your simulation. Okay, so this will be your voltage waveform for input and output, and then this is your current waveform for output. Okay, so and then this is the reading for your IRMS, VRMS, and then V average and I average. So you can fill in your table here. Okay, so 90 degree time delay is 5 millisecond. So this one refer to your measurement probe. Okay, so complete this table by repeat the procedure number 5. Okay, and then okay, sketch the output and input of your voltage and also output current for firing angle of 90 degree. So you only need to attach one waveform for output voltage, input voltage, and output current only for 90 degree firing angles. Okay, so I think that's all. So and then for the discussion, you need to calculate a few more parameter here. So refer to all the formula attached here. Okay. And then you have to plot the relationship between firing angle, PAC and PDC in this graph. And then do the discussion and then the conclusion. So these are the related formula you have to use to find new parameter here. So this one, okay, so how to get the V input RMS and I input RMS? So you have to place one more measurement probe at the input. Okay, because this is your measurement at the output and then this is your measurement at the input. So just run and then all the data is displayed here. Okay, so that's all for lab 2 briefing. So any question you can ask me. So assalamualaikum and thank you.